All right, let's go ahead and get started. So, hello everybody, and welcome to today's webinar presentation, DevOps 101, Introduction to Containers, brought to you by JFrog. I would like to introduce you to our presenter, Melissa McKay. Melissa's background and experience as a software engineer spans a slew of technologies and tools used in the development and operation of enterprise products and services. She is a mom, software engineer, Java geek, huge fan of unconferences, and is always on the lookout for ways to grow and learn. She has spoken at Code One, Java Dev Day Mexico, and is part of the JCree and JAlba unconference teams. She is currently a developer advocate for JFrog Incorporated. I would like to do a quick sound check for Melissa. So Melissa, please say hello to our audience. And audience, let me know if you can hear her by posting a message into the chat panel.
Hi, everyone. Can you hear me okay?
And
Awesome.
Looks like we're good to go. And I'd like to pass it off to Melissa for the presentation.
All right, great. I do want to reiterate, I do come from a developer background, have been doing that for close to 20 years. So that is where a lot of my talks stem from, where a lot of my experience comes from, and that's my passion to talk about, and especially with getting junior devs and engineers just started and working on their projects. I've been on a lot of different teams, large teams, small teams, big companies and small companies, and had my share of frustrations and successes like a lot of you, and definitely on my way discovered a passion for speaking. And that was something I did on my own time for a lot of years, and I finally decided to make the leap and go to JFrog and become a developer advocate. So this is something I do regularly now. I know everyone here is stuck at home. We're all frustrated and getting a little bit of digital, virtual fatigue from all of this, but I really appreciate you being here, and I'm really excited to talk with you today about virtual containers. So this is actually my first time using this particular webinar platform. So I want to exercise the Q&A panel a little bit and ask you all a question. This is something I ask just about everyone I come in contact with, is how are you using containers today? For some of you, containers are brand new. Some, this might be old hat and just review, but I'm really curious how you're using them, if you're just using them in your local environment, or a particular test environment, or if you're actually using them in production. So take a minute. You can choose, either or all of these answers, and let me know how you're using containers. All right, let's get started. First, I'll give you a brief history to give you some background context. Hopefully this isn't too boring, but history is super important. There are some milestones in the past that are important to know to give you this background that you need. Then we'll take a look at the container market and what's been happening there over the last few years. You'll see some interesting things. Then we'll move into getting a real understanding of what Docker actually is. Docker is not synonymous with containers. You'll learn that today. After that, we'll be in an excellent place to talk about what a container actually is. Then we'll review a few gotchas with containers that you might fall into if you're just getting started. Then I'll talk to you a little bit about an option for managing your container images. And last but not least, I'll point you to a link where you can get some hands-on interaction and a JFrog t-shirt. Those of you that are familiar with JFrog t-shirts, they're pretty awesome, so don't miss out on that. Without further ado, let's jump in and start learning about containers. Now, right away, I know some of you are wondering if you're in the right talk, because here you see a picture of bananas, which obviously is not what you would be expecting. So I am on a bit of a rebellion. I refuse to show any pictures of shipping containers in my container talks. I'm tired of seeing them. So you won't see any shipping containers in this talk. The second reason I chose bananas is because this is a story about how our industry has adapted to dealing with limited resources over time. And a story that my grandfather told me repeatedly growing up was, it went like this. He and his siblings would receive a banana for Christmas. This was a once-a-year treat, and they would scrape the banana peel to make sure they could get all of that banana off. This must have been, in the late 20s, early 30s when this was going on. So they made sure that none of that banana would go to waste. And now that's probably not the best analogy, but like I said, this is a story about how computing resources are scarce, and especially in the 1960s and the 70s, they were very limited and very expensive. On top of that, it took forever to get anything done. Often a computer would be dedicated for a long period of time to a single task for a single user. So obviously the limits on time and resources created a lot of bottlenecks and inefficiency across the board. And just being able to share those resources isn't enough. There needed to be a method to share and also not get in each other's way without having one person inadvertently cause an entire system crash for everyone else. So necessity is indeed the mother of invention here. The need for better strategies and sharing compute resources actually started a path of innovation that we see massive benefits from today. There are some key points in time that brought us to the state we are in today with containers. And I'm going to begin our history lesson with chroot, or some pronounce that change root. Chroot was born in 1979 during the development of the 7th edition of Unix, and it was added to BSD in 1982. Being able to change the apparent root directory for a process and its children results in a bit of isolation in order to provide an environment, for example, for testing a different distribution. Chroot was a great idea and solved some specific problems, but there was more that is needed. The jail command was introduced by FreeBSD in 2000. Jail is a little more sophisticated in chroot in that it includes additional features to help with further isolation of file systems, users, and networks. And it had the ability to assign IP addresses to each jail. That was pretty significant. In 2004, Solaris zones brought us ahead even further and gave us an application full user process and file system space and access to system hardware. Solaris zones introduced the idea of being able to snapshot a file system. That is an also pretty significant move. Moving on, in 2006, Google jumped in with their process containers. This was later named cgroups, which you'll hear more about cgroups later. These cgroups centered around isolating and limiting the resource usage of a single process or a collection of processes. Moving right along, in 2008, cgroups were merged into the Linux kernel, which along with Linux namespaces led to IBM's development of Linux containers. 2013 was a big year. Docker came on the scene, bringing their ability to package containers and move them from one environment to another. The same year, Google open sourced their project called Let Me Container That For You, which provided applications the ability to create and manage their own subcontainers. And it's here that we saw the use of containers and Docker specifically explode. In 2014, Docker chose to swap out their use of the LXC toolset for launching containers with libcontainer in order to utilize a native Golang solution. So this was an interesting tidbit of information. Docker is written in Go. And I'm almost done with the history lesson, because from here on, you would start just seeing a ton of names of projects, organizations, specs, etc. that tend to be confusing if you don't have a better understanding of how containers work, which is the point of this talk. Another event, however, in June of 2015, this one is important to know because it will give you some insight into the activity and motivations behind shifts in the market around containers. The Open Container Initiative was established. This is an organization under the Linux Foundation that includes members from many major stakeholders, including Docker, with the goal of creating open standards for container runtimes and image specification. This is supposed to open the market for a little bit of competition, which we'll look and see what happens. So while all this is going on in the background in the container world, like I said in the beginning, my background is in development and my heart is with Java. So something to note is that in 2011, in July, Java 7 was released, and work was started on Java 8 in March of 2014. So keep this in mind, especially if you're a Java developer and you're working on containerizing your Java applications. This little bit of history will be important to know, and I'll bring it up again later. So that's it for our history lesson. Let's take a look at what's been going on in the market as far as container runtimes go. I did some hunting, and I found that for the last 3 years, Sysdig, which is a company that provides a really powerful monitoring and troubleshooting tool for Linux. If you're in DevOps, you're probably very familiar with this tool. They put out a container report based on the analysis of their own users. And part of the report includes data on container runtimes that are in use. So starting in 2017, they analyzed data from 45,000 containers. They didn't bother putting a graph in that report because 99% of those containers were Docker. So obviously they didn't split up the results. In 2018, however, they analyzed twice as many containers, 90,000. 83% you can see is Docker, 12% CoreOS Rocket containers, 4% Mesos Containerizer, and only 1% LXC. So it looks like other container runtimes are starting to encroach a little bit, but Docker still has the bulk of the market share here. In 2019, this is the last report that's available from Sysdig, they analyzed 2 million containers. So you can see right now the explosion in this market. Docker is still holding relatively strong at 79%. 18 is Containerd, but it's worth noting that Containerd is a runtime that Docker actually builds on top of. The last 4% is Cryo. So I don't know that there's enough data here to determine whether Docker will actually stay on top in the future or if something completely different is going to come around. That remains to be seen. But this data is interesting, especially because of what's been happening over the last few years. And notice right away the disappearance of Rocket. That's kind of it's a sad story because it's a CoreOS project. It was acquired by Red Hat in the beginning of 2018. And prior to that, it was accepted to the CNCF as an incubating project. It looked like a promising competitor to Docker's Containerd. However, since that acquisition, the development of the project went dormant. And in mid-2019, Rocket was archived by the CNCF. In February 2020, the project was ended. So Docker still has it. And now that I've introduced a few of these other container runtimes that exist out there besides Docker, it's time to start talking about what a container actually is and what Docker actually provides you in order to appreciate those differences. What is Docker anyway? Like I said before, Docker is not synonymous with a container. It's a tool that most people working with containers are familiar with. And this is key. What Docker had over the other players in the container game was a focus on commoditizing a complete solution that made it easy for developers to package and deploy their applications. So once containers became easy to use, we witnessed that explosion of tools and resources around containers, and the Docker image format rose to become the de facto standard in the market. The stats that I showed you previously from the Sysdig reports are specific to container runtimes. That terminology is important to understand here. And I'll explain the pieces and parts involved with working with containers, and you'll immediately understand why Docker sucked up the market so quickly. So as users, let's think about what we actually need to get our apps out there and running. Every innovation that is coming out of this space is purely based on what users need or want, whatever the motivation is behind it. If a user needs or wants something bad enough, there's a huge opportunity out there for solution providers like Docker. That seems like a common sense thing to say, But so sometimes, we find ourselves getting so far down into nitty-gritty details that we lose the actual problem we were trying to solve. And this leads to a ton of missed and overlooked opportunities. Docker did not miss this opportunity. So here's a list of needs broken up into discrete features. First and foremost, we need that container itself. Some of you might be asking about virtual machines at this point, and discussing VMs is out of the scope of this session, so I'm not going to go deep into the differences there or why you would use one over the other. But one thing I will say is that a virtual machine is not a container. The biggest difference being that a VM, a virtual machine, includes an entire OS all to itself. Containers share the system's OS. And the point of the container is to be lightweight and to have the ability to move from one environment to another seamlessly and quickly. So being able to share that OS is pretty important. That said, I know there are developments happening in the VM space, but that's a topic for another time. So the rest of this list. We need an image format to define a container. We need a way to build an image of a container, a way to manage those images, a way to distribute and share those images, a way to create, launch, and run a container environment, and a way to manage the life cycle of the running containers. And I didn't even get into orchestration or anything like that, but this is plenty to prove my point about Docker. So Docker was ready with an answer for everything. You want to start using containers? Use Docker Engine. You need an image format? Here's the Docker image format. You need a way to build an image? Use a Docker file and call Docker build. You want to manage images? Call Docker images or Docker run, remove. You want to share your images or use an image from someone else? You can use Docker push, Docker pull, and there's Docker hub where you can easily store and share your images with everyone. If you need a way to launch, run, and manage your containers in their lifecycle, call Docker run, Docker stop, Docker PS. Docker succeeded quickly in meeting the immediate needs of a container-hungry market. And on top of that, the tool sets that Docker provided made it all extremely easy for developers to wrap their heads around, start using immediately. It was enough to walk away with a tremendous part of the market share all the way down the aisle. I hope you appreciate this banana picture. It seemed, pretty relevant. So remember in our history when I spoke about the Open Container Initiative, out of all of those features that I just discussed that Docker offers, there are 2 of those that were taken up by the cause, for the cause by the OCI, the image format and the container runtime. So there's that terminology to pay attention to. Docker did quite a bit of reorganizing their entire code base and developing abstractions and pulling out some discrete functionality. And they are a heavy contributor to the OCI, giving the Docker v2 image spec as a basis for the OCI image spec, and run C, which was contributed as a reference implementation of the OCI runtime spec. So the OCI image spec, that takes care of your images. The run C is the open implementation of the runtime. There are quite a few other container runtimes you might see out there. We already saw a few of these. That's Containerd, Rocket, Cryo, Kata. All of them have various levels of features for specific use cases. And it's worth, pointing out Containerd was contributed by Docker to the Cloud Native Computing Foundation. It internally uses run C. Containerd has also been integrated into Docker and has been used since version 1.11. So it's been out there a while. That came out in 2016. The next few years will be interesting to observe what happens with these specs and how the OCI moves forward. There's quite a range of differing opinions about what should and should not be in the standard for a container runtime. And we're in a situation where using a runtime alone that just meets the requirements of the OCI spec, it doesn't seem to be enough to pull folks away from Docker and use something else. I've added a couple of links here that are excellent starting places to learn more about container runtime specifically, if you're curious. The second one is the beginning of a blog series by Ian Lewis, who's a Google Dev advocate. The first subtitle in that blog is what attracted me the most. It's literally, why are container runtimes so confusing? And I read that and agreed immediately. So Ian does a really good job of succinctly explaining some of that. Now that you understand what Docker entails and some of what's going on in the market, let's focus on just the container itself and what that actually looks like on your system. I'll show you how it's stored and what's happening under the covers. You'll discover pretty quick that images and containers aren't really all that magical. My first experience with containers was as a new developer on a project with a tight deadline. Of course, that describes most projects. The best course of action for me is usually just to jump in and just get started. I want to get something up and running on my local machine, and I learn best by just doing. The Docker documentation is actually really good for this. Highly recommended. If you find yourself in a similar position, definitely go to their Get Started docs, and I have a link to those here. And going through that guide will get you comfortable with some of the Docker commands that you're going to need. The first thing to note is that a Docker image is really just a tarball of a complete file system. When an image is unpacked, it's just thrown into its own directory, which becomes its root file system. The second is that the processes that are involved in running the containers, they're just regular Linux processes. On top of that, there's just a few Linux features that are used together in a way to achieve that isolation that we want from containers. Namespaces are one of those features. That's an important ingredient because this is what's used to provide virtual separation between your containers. This is how the processes inside a container don't interfere with the host or processes inside another container. These are some that are running on my box right now. You can see these namespaces were set up for a Postgres container that I have. The cgroups functionality is integral to constraining how much a container can use things like CPU, memory, network bandwidth, etc. I can set those constraints by including options on the Docker run command when launching an image. Here you can see I've constrained this one. I've constrained the memory usage limit on one of my containers. I'm going to gloss over some of the file system details that are interesting to know, where containers and images are actually stored on your file system. First off, after you've installed Docker on your system, running the command docker info will spit out a whole bunch of information about your installation, including the Docker root directory. This is where most everything you're going to care about regarding your Docker images and containers will be stored. Note that if you're on a Mac, which I am on a Mac, your containers are actually running in a tiny VM. So you're going to need to use a screen or some tool like that to get in there and get to the Docker root directory to look around. If you're not familiar with how to use that command, if that's new to you, definitely Google Mac screen. Get familiar with it first because it will mess up your text display pretty good if you don't enter and exit it in the correct way. This slide shows how you can get information about the images that you have stored on your system. First, I listed my available images using the Docker images command. And I actually have several images installed, but I'm only showing you the first couple in this list. Using the Docker inspect command, I can inspect any image I like using its image ID. This will spit out a ton of interesting information. But what I want to highlight here is the graph driver section, which contains the paths to the directories where all of the layers that belong to this image live. Docker images are composed of layers, which represent instructions in the Docker file that was used to build the image originally. If you take a look at a Docker file, every line counts as a layer. These layers actually translate into directories. and they can be shared across images in order to save space. The lower dir, merge dir, and upper dir sections are especially important. The lower dir directory contains all of the directories or layers that were used to build the original image. These are read-only, important to remember that. The upper dir directory contains all of the content that has been modified while the container is running. If modifications are needed for a read-only layer in lower dir, then that layer is actually copied into upper dir, where it can be written to. That is not read-only. And this is actually called a copy on write operation. When you start getting familiar with Docker, you will come across that term frequently. It's important to remember also that the data in the upper dir is ephemeral data. It only lives as long as the container lives. So in fact, if you have data that you intend to keep, you should utilize the volume features of Docker and mount a location that will stick around even after the container dies. This is how most containers handle running and storing data to a database, for example. Lastly, the merged dir is a kind of virtual directory that combines everything from lower dir and upper dir. The way the union file system works is that any edited layers that were copied into upper dir will overlay the layers in the lower dir. This is when you get into a container, this is everything that is visible to you as the user of that container. This slide shows that I actually have a few containers currently running on my system. 2 of them are my local JFrog Container Registry installation. That includes a container for ARTIFACTORY and a container for a Postgres database. The other is just a simple test container I was playing around with. Note that the container IDs of the running containers match up with the container's subdirectory names. Something to remember here is that if you stop a container, that corresponding directory doesn't automatically go away until the container is actually removed with the docker remove command. So if you have stopped containers lying around that never get cleaned up, you might see your available space start to dwindle. There's a docker prune command that you can run to help clean stuff like this up. Or when you launch a container, you can launch it with a flag to indicate that it should be removed when it's finished. And I do have an example of that. There's the example of the flag. This is something that can also be handled by whatever orchestration. If you have like a Kubernetes environment, for example, it can handle the actual getting rid of these containers. The tool sets around building and running images and containers have made things so easy that it's also easy to shoot yourself in the foot in a few places, which I have certainly done. Here are 3 of the most common gotchas. Plus, there's one JVM specific gotcha that I ran into almost immediately when I first started working with containers. The first is running a containerized application as the root user. I'll be honest here, when I was initially getting containers up and running, I was just so excited about how well it was working that it took a while before I took this one seriously. And now that you know that the processes inside a running container are just like any other process on the system, albeit a few constraints, it's scary now to run as root inside a container. Doing that opens up the possibility of a process escaping the intended confines of the container and gaining access to host resources. You really, really need to reduce the attack surface of your container by following the principles of least privilege. Although containers are designed not to affect other running containers, if someone actually gains access to that container and immediately has root privileges, they can wreak havoc on the host. So how do we mitigate a problem like that? The best thing to do is to create a user and use the user command inside the Docker file when the container is built. And that will allow the processes to run as that user. There is a way to specify a user with the Docker run command, but that leaves open the possibility of forgetting to do that. And it's nice if the image is set up by default to not run as root. That reminds me, pay attention to the official images that you pull from Docker Hub. Sometimes they might just run as root by default, and they actually leave it up to you to figure that out. So be careful with those. The next one, even though Docker provides you with the ability to set your resource limits on your container, it doesn't automatically do that for you. In fact, the default settings are a free-for-all with no limits anywhere. So make sure you understand the resource needs of your application. Too little and your container will die from starvation, and too much and your container will smother others on the system. The resource usage of your containers is something also that you're going to want to monitor over time and adjust as needed. And you need, operations help probably to do this. It's a good way to determine if something is going wrong or if load on your system has changed for any reason. This is a pretty big security issue. Never updating. It's easy to get complacent and not pay attention to what is actually being pulled in when you build images. Not only do you need to be aware of outdated versions you specify in your Docker file, but you need to pay attention to what's in the base image it's coming from. Not updating those packages and libraries inside your container can lead to some pretty embarrassing results, especially when there are tools available out there, readily available now, that will alert you when security issues have been discovered with specific artifacts. So even, making all those precautions and ensuring that you're running containers with a non-privileged user, even that has risk when there are known vulnerabilities that exist within your container or even on the kernel of the host. From time to time, there are exploits that are found that enable attackers to potentially escape a container and cause some problems. So keep up with those security updates. I've been on teams in the past where that has not been a priority. And most of the reason for that is because you might be on a particular service or working in a particular product or service that you're just afraid to break. That is a symptom of completely different problems. Trust me, it is much worse to leak private data or potentially be the start of a domino effect that can bring down an entire system versus updating your packages and keeping up with those security updates. So this one is very Java specific, specific to containerizing Java applications, and very much related to being aware of what your application requires to run successfully regarding memory. And remember earlier in our history lesson when I mentioned the dates for Java 7 and Java 8? Well, the JVM is pretty clever at automatically determining settings for your swap and your heap and your garbage collection behavior based on things like the memory and the number of cores available on your host. But considering the timeline of Docker and Java releases, especially Java 7 and 8, certainly earlier versions, they are not fully container aware. This means that your Java application won't necessarily obey any memory and CPU constraints that you put on your container, and you may end up with some surprises, some surprise out of memory killer activity. The reason for this is just simply that the mechanisms that the JVM uses to retrieve the available resources come from the actual host machine and not the C group limits like you would expect. There were quite a bit of improvements made to introduce container awareness in Java 8, specifically update 131. Definitely further improvements in later versions, but if at all possible, you really should get to Java 11. That's the latest available LTS release that is container aware. If you're stuck on a legacy version though, because I know I've definitely been on some projects that just were not ready to advance from Java 8, all is not lost. You just won't be able to depend on the JVM automatically determining the best use of resources for you. You're going to need to launch those applications with the necessary flags that you need to tell it how much memory, number of garbage collection threads, things like that, based on the limitations that you want to set for your container. So speaking of tools that can help you manage your images, JFrog Artifactory supports Docker registries and images. You can use it just like you do for other types of artifacts, both as a cache for third-party base images and as your own internal registry. So I didn't know this years ago as a developer. When I used Artifactory for a lot of my other packages, I didn't realize that I could use it as well for Docker images. After uploading those images, you have the ability to gather statistics, and you can even drill down into each layer of an image for more information. If you've integrated a CI/CD solution, you can also determine what build produced a particular image, or even what builds used that image. All good information to have. We also, we discussed earlier the problems with not updating images regularly, and I want to introduce you to XRAY, but let's talk a little bit more about why we care about image security. Those base images that I mentioned earlier, it is really, really important to know your build, know how your build is put together, know where everything is coming from, and have that inventory, be accountable for it. There are all kinds of third-party dependencies that we use. A lot of projects, you are not writing everything from scratch. You're using a lot of stuff that's already out there, especially open source software, that kind of stuff. And a lot of those have known vulnerabilities associated with them. There are huge databases that collect this information, and XRAY is an example of a product that uses that information to let you know when there's a problem. On top of security, it can also handle licensing. That's the other thing that you need to be concerned with when you're pulling in third-party images and all of the associated packages. There may be licenses in there that don't work with your company's policies. So it's important to know what all of your inventory that you're using for your builds, what the licenses are. XRAY can help you manage those as well. XRAY is the security scanning tool that is available within the JFrog platform. It alerts you about any known security vulnerabilities and licensing issues. And for Docker images, it's really cool because it has the ability for you to drill down into the layers of the image and find exactly which library or package has been flagged as a problem. Pretty powerful. You also have control over how sensitive these alerts are and what actions you want to take when they're triggered. All right, that is all I have. Thank you everyone for coming. I really hope you enjoyed this webinar and that you got something out of it to take back to your teams, or that you just learned some detail that you didn't know before. Before we move on to Q&A, I want to share this opportunity with you to take the JFrog Platform Docker Challenge. This is a link you can go to. You can sign up for a free account and be able to, look around in there and play with things. You'll get some instruction on how to set up Docker registries and be able to, not only create them, but use them and get some hands-on practice. All right. I'm going to take questions now if you have anything that you would like to ask. All right, here's one that pretty common question. What's the difference between a container and an image? And I know sometimes I tend to use those interchangeably, but they really are different things. An image is actually a static blueprint that a container is created from. If you have any development background at all, if you're familiar with object-oriented programming, an image would be the same as like a class file, and a container would be an instance of that class or object. A container can be launched, it can be stopped, it can be started, it can be destroyed. The image is just the blueprint plan of how to recreate that image or that container. All right, another question. What's the difference between a Docker registry and a repository? These are also terms that can be really confusing, especially repository. You hear that word all the time. There are code repositories, there are artifact repositories. It basically just describes a collection of things. A registry, which is normally what you hear specifically with Docker, a Docker image registry, that is really just a collection of repositories. And a repository is a collection of all of the different versions of a particular image. So hopefully that helps explain that a little bit. Within the JFrog platform, it can be a little confusing because they are used interchangeably, and it's just because registry versus repository, it really is just an organizational thing, and you can have multiple registries with multiple repositories set up in ARTIFACTORY. Here's a good one. Is there a way to prevent usage of images that have known vulnerabilities? So yeah, we talked about now that you know whether an image has problems or not, and it's living in your repository of images, how does this help you? Well, you can actually view what the problems are in the interface itself, but you can also set up restrictions on the use of that image. You can also require, like, let's say this is a brand new image and it hasn't even been scanned yet by the vulnerability tool. You can require that before that image is downloaded, it must be scanned. So it could be the first developer that retrieves that image from the repository that will initiate a scan of that image before it's used by the developer. There are lots of other levers and controls that you can put in place. What you don't want to do is set them all and prevent anyone from doing anything. So you would want to start with a good rule set on what's important to you, what is make or break, and what you can let slide a little longer. It's helpful with the XRAY information. You get a pretty decent description of what problems are, so you can decide to pick which ones you want to pay attention to, which ones you don't. Even the levels of severity, you can choose those as well. All right. Anything else? Okay. If we push a Docker image to ARTIFACTORY, does ARTIFACTORY push Docker images to the Docker Hub in the back end implicitly? So I'm hoping I understand this question correctly, but what's actually going on is if you have a registry like ARTIFACTORY and it's between you and a remote registry like Docker Hub, and there are lots of reasons you would want to do that. It could be network access, it could be availability. You want to make sure that you have access to your images that you need for your builds, even when a remote registry might not be available. So what's happening is when you pull an image from a remote resource and it's the first time, that image actually gets stored in a cache, and that ARTIFACTORY serves as that caching level. So then every time after that, anytime a developer requests, or a build system requests that image, they're going to get it from the cache. As far as pushing images, normally you would only push the images that you're working on. You would normally just push those to a local repository. Those aren't just automatically pushed to a remote repository. All right. How does JFrog help see resource usage across containers and environments? This is a good question, not just for JFrog specifically, but something that you really should be tracking and be aware of. Know where your images are being used, who's downloading them, who's using them, what environments are they being used in. JFrog specifically, at least the ARTIFACTORY portion, you can set up various permissions for each of your registries and repositories, and you can control who has access, what environments have access. These are really important so that you can prevent things like accidentally pushing a test image out to production environments. That's a good example. That might be one reason you would want to divide up your repositories between your environments that you're using. In the GUI, there is the ability to see how many downloads have been performed and from what repositories. There's also other tools out there. So I don't know if any of you are familiar with Splunk, but we do have integrations with programs like that. In fact, one specifically, it's called JFrog Platform Log Analytics. And it actually is an integration that you can put in that will pull all of this information from the Artifactory logs, and it will tell you even the IPs that requests are coming from. So you can detect bad actors. You can also detect logins, maybe invalid logins or problems with someone remotely trying to access images they aren't allowed to, that kind of thing. All of those are really important to have observability in your system. All right. I'm pulling up, seeing if there's any other questions. Lots of questions about recording of the session and slides. Those, my understanding, those will be made available to you after. And that is about it. Oh, here's one. Are multiple containers of the same app function usually run on the same host? The idea of containers is really when microservices came out, and the idea is to break up an application into all of these little pieces that you can individually scale and make your system either more reliable or more efficient or more performant. And so yes, it is very common to have a tiny little service that is multiplied over and over on the same host. There are orchestration systems like Kubernetes, which will help you manage that and control that, because obviously you can't, you've got to have some limits. You can only have so many containers that need a certain amount of resources on a host. So you definitely still need to do the math and figure out what's possible. But yes, this is very, very common and very commonly used even in cloud environments when you're operating with bursty load or bursty traffic. You need to have that ability to be able to launch new containers of a service. All right. That is all I have. If there's something that I didn't get to or I didn't answer, I will go over these questions again and I'll reach out to you individually. Thank you again, everyone, for coming. And I'm going to pass it back to Drew for closing remarks.
Thanks, Melissa. DZone itself would like to thank you for a wonderful presentation. DZone would also like to thank JFrog for providing the audience with a great webinar. Lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career. Thanks and have a great day.